Hello, this is our CS230 course presentation on the topic Cache Hierarchy Optimization for Graph Analytics. Our team members are Isha Arora, Shantanu Welling, and myself, Karan Godara. This is the baseline cache configuration that we aim to improve upon. We use the trace BFS14 and SSSP14 and LRU as our base replacement policy. No prefetcher was used in this baseline configuration. We first learned about graph data types and data layouts in graph analytics traces, and that is the key in understanding the behavior of memory accesses in data analytics and thus optimize cache configuration for them. One of the most widely used graph data layouts is the compressed sparse row CSR representation. The CSR format consists of three main components: structure data. It comprises the neighbor ID data. An index of this array corresponds to a unique vertex V and points to the start of the list of V's neighbors. In the case of weighted graphs, each entry in the neighbor ID array also includes the weight of the corresponding edge. Second, property data. It comprises the vertex data array. The vertex data array stores the property of each vertex and is indexed by the vertex ID. Third, intermediate data. It comprises any other data like the offset pointers. Each entry in the offset pointers belongs to a vertex and points to the start of its neighbors in the neighbor ID array. It is generally observed in graph analytics traces that property data has long reuse distances and structure data has short reuse distances. Thus, as a whole, graph analytics traces have irregular memory accesses. We started off by initially analyzing the results on the traces when using our baseline cache configuration. We observed that the hit rate of L1 is considerably higher than that of L2 and LLC, and thus we first started off by changing the sizes of L2 and LLC. Changing the size of L2 didn't yield any improvements, as can be seen by this graph, but changing the size of LLC yielded improvements. From this, we inferred the general behavior in graph analytics that either the reuse distance of data is short and thus the data is served in the L1 cache, or the reuse distance is large such that neither L2 nor LLC have the data and the data has to be brought from DRAM, thus stalling the processor, which accounts for the low IPC. Increasing the size of LLC increases the IPC, as then the data with long reuse distance is able to fit in the LLC. But as L2 is smaller in size, long reuse data can't fit in it, and hence increasing its size doesn't increase IPC. So then we thought if changing the way data is kept in the cache would yield better results, and hence we experimented with different cache hierarchy policies like exclusive and inclusive and compared their performance with the default cache hierarchy in ChamSim, that is non-inclusive. We saw that non-inclusive works best. This can be reasoned out as a non-inclusive cache hierarchy allows for more flexibility in the use of the cache. Therefore, we do further test on the non-inclusive cache hierarchy. Thus, we inferred that it is not the way the data is kept in the caches, but the type of data that is kept, which is serving as a bottleneck in improving performance. So the question arises, what can we do to improve cache performance? How to make sure that reuse data stays in the cache? How to increase hit rates? The immediate idea that come to our mind to solve this was to employ better cache replacement policies for graph analytics. The other question we pondered upon was how to utilize L2 that is being underutilized at present. The immediate answer that struck us was to use prefetchers.
So we experimented with various replacement policies. Some of them were heuristic, that means they were based on a set of rules or guidelines that dictate which cache block to replace, and the others were non-heuristic, and hence used a more systematic or deterministic approach to select the line to it. The heuristic ones were MRU, FIFO, LFU, random, LRU, DRIP, SRIP, and the non-heuristic ones were SHIP, Hawkeye, and Mockingjay. SHIP computes a signature for each cache block based on its memory address and access history, and uses this signature to predict whether the block will be accessed again in the near future. Mockingjay selects the line with the highest predicted expected time of return as the replacement candidate. Hawkeye attempts to mimic Velarde optimal policy by observing past memory accesses and does a PC-based prediction replacement. We observed that the non-heuristic policies perform better than the heuristic policies. This can be reasoned out as graph analytics have irregular memory access patterns. As heuristic policies work well for accesses that follow specific patterns, they don't work well in graph analytics. These were the general trends in replacement policies. Now moving on to prefetchers. The first question that arises is, if we prefetch, where to? We decided to prefetch in L2 as from previous observations, L2 was being underutilized. Hence, prefetching in L2 would reduce cache pollution and also serve as a technique to make the underutilized L2 cache useful. These are the prefetchers that we tested. Next line, Bertie, signature path prefetching, T-skid, bouquet of prefetchers, Sangam, best offset prefetchers, and Pangloss. Each brought something different to the table. As Mockingjay was performing the best among the tested replacement policies, we tested prefetchers with Mockingjay replacement. We observed that Pangloss and best offset prefetchers were the lead runners, and hence we focused our attention mainly on them. We started off by trying to specialize Bob for graph analytics. Our first idea was non-timely. Sometimes prefetch accuracy and coverage can take a toll if we only consider completely timely prefetches, as in the original implementation of Bob. Hence, we attempted to reduce the trade-off between timeliness and accuracy by considering non-timely prefetches too, by inserting X on the left side of the recent request table as soon as X plus O is demanded. Our next idea was fetch more. To satisfy irregular memory demands of graph analytics traces, we increased the prefetch degree from 1 to 2. As we have a prefetch throttler already in place to prevent cache trashing won't be an issue. Our third idea was multiple. To improve cache performance, instead of testing for only one offset per iteration, we tested for multiple offsets in each iteration. Our fourth and final idea for Bob was foresight. As graph analytics memory accesses often have long reuse distances, so we increased the list of offsets that we are testing for from 46 to 56 to increase possible prefetch distances. As can be seen in this graph, fetch more optimization worked best, and hence that is the optimization that we further worked with. We also increased the performance by also prefetching in the L1 cache along with L2.
We then compared Pangloss with our improved fetchmore version of best offset prefetcher, and we can see that our changes helped to achieve better results. Next, we focused our attention on optimizing non-heuristic cache replacement policies. They were performing better than the heuristic ones, and hence we decided to specialize them for graph analytics. We began with attempts to specialize Hawkeye. In the absence of cache averse lines, Hawkeye employs LRU approach. So we experimented by employing other policies to see if we can make a difference. We implemented FIFO and LFU policies in the absence of cache averse lines. Unfortunately, we saw no improvement. This can be reasoned out as LRU, unlike the others, takes into account the temporal locality principle and thus provides cache hits when memory accesses have temporal locality. Hawkeye differentiates between demand accesses and prefetch accesses, and it ignores redundant prefetches. This maximizes cache utilization, but it can drastically increase prefetch traffic in some cases. Therefore, to check if memory traffic was the bottleneck, instead of treating these accesses differently, we modified the code to treat them the same. But this again gave us no improvements. The insight that we gained from this is that memory traffic is not the bottleneck in graph analytics. As we can see from these results, the ideas didn't work. Our third idea was to increase the associativity of caches when using Hawkeye replacement policy. A higher associativity gives replacement policy more options to choose from. And since Hawkeye is making more informed decisions than the other policies, we speculated its advantage should grow with higher associativity. We saw improvements when we doubled the associativity, which aligned with our speculations. This idea worked. As we have come to know that heuristic-based cache replacement policies don't work well for graph analytics, a future prospect is that we can see to specialize Hawkeye for graph analytics is that instead of using a heuristic-based cache replacement policy in the absence of cache averse lines, using prefetch-aware non-heuristic cache replacement policies may lead to improvement. We then attempted to specialize Mockingjay by tuning its hyperparameters. Firstly, we tuned the penalty factor, which is the factor by which the estimated time remaining ETR for the next access of that line is scaled. The line with the highest ETR is given the highest priority to be evicted. This way, we discourage Mockingjay policy from caching demand prefetch or prefetch usage interval blocks, thus making better use of the limited cache, which works well for graph analytics, as can be seen in these results. Nextly, we tune the max RD parameter, which defines the highest allowed ETR prediction, which is not treated as infinity. Reducing it makes Mockingjay policy to evict lines with small reuse distance with less probability compared to those with higher reuse distance. This again favors the reuse of memory accesses for graph analytics traces, and thus we see a speed up on decreasing this parameter, as can be seen in this graph. After this, we finally compared our best to replacement policies, Hawkeye, and our improved version of Mockingjay, and observed that Mockingjay is performing better. Now, keeping the replacement policy fixed as Mockingjay, we compared our optimized best offset prefetcher and Pangloss and saw that the results are trace dependent. With this, we end our presentation. Thank you.